It gives me really great pleasure to welcome Dr. Lamin Juwara today, who is a graduate from Quantitative Life Sciences. He graduated in May, right?
Yep.
May. And he was, made his way through the program extremely quickly. And worked on a topic that is of really important interest today, talking about data and how it can be used, how it can be generated. So he is now working at Children's Hospital of Ottawa and affiliated with the University of Ottawa on this particular topic. And we are really happy to welcome him here today in person to give us a talk. Welcome, Lamin.
Thank you. Thank you so much for the kind introduction. I am happy to be back here. So just to start, the title of my talk is on mitigating the impact of data bias through synthetic data generators.
We have to click on.
Can you hear me? Oh, no, I think that's on Alex. Yeah.
We can hear you.
No,
Good.
no, hasn't helped.
We can hear you.
We're not talking about the sound, we're talking about the video.
Oh, it was working on system recording. I think you have to put your cursor off the screen.
Yeah, on. Yeah, you have to move it onto the second. Yeah.
Oops.
Small
Sorry.
technical challenge.
Yeah.
So I'm able to see your cursor on the left.
No, I'm not able to.
You have to do it on the screen here. Projector while you use the cursor.
Oh, yeah, do it right here. There you go.
Got it.
Okay.
All right.
Okay. So just to give a quick outline about the talk today, I think I'll start with by giving an introduction of what I mean by data synthesis, and then I'll follow this by going over like some of the foundational material that is necessary for understanding how this data could be generated, and then I will present to you some use cases. In particular, I will look at use cases that has to do with data bias. I think I'll spend a bit of time just going over data bias, like the kind of bias that we are interested in, and what approaches are available for mitigating the bias and how they could be induced. And then I will go over like various approaches that have been proposed for mitigating data bias in biomedical research. And then I'll present to you the approach that is proposed in this project. And then I'll close by showing some applications to both synthetic, through both simulations and real data examples. So just to start off with an introduction of synthetic data generation. So formally, synthetic data is defined as artificial data that is produced in order to either substitute or enhance some real data. This is often for safeguarding personal information, so privacy purposes, or it could be for mitigating bias or improving on AI models. So how does the data synthesis process work? So at a very high level, this is essentially how it works. So you always start off with some real data source, and then you basically propose a model, let's say F, that is good enough to fit that data. If this model is good enough, then essentially given a new set of data, you should be able to predict the target. Now, that combination of new data and the target gives you what would be considered as synthetic data, right? And so you could go on to basically fine-tune the data and make sure that essentially that this new data and the old one are as close as possible. So that is to say that that is essentially basically just to say that all of the properties that are inherent in the original data are still preserved in this new data. Okay. So just to give some background about some of the foundational material that is like useful. That is useful. So the first one basically has to do with this old paper by Robin, where he basically proposed that you could essentially like release multiply imputed like data as a surrogate for like for this. Okay, so just to give a so let's say, for example, we have some tabular data with some non-responses given by NA here. Typically, when you're interested in doing like data analysis, there's a couple of ways you can go about this. The easiest way, for example, might be to just do like a complete case analysis. So that will essentially involve like removing these observations, right? But we know that that is not always efficient. And in fact, at worst, you can come up with estimates that are completely biased. So over the years, people have suggested like doing maybe like a single imputation, but again, we know that that has its own problems. So this builds on a previous work by Robin, where he basically proposed to do multiple imputation. So basically, you can generate multiple copies of the data set, and then do analysis on each one of them, and then combine the overall result through a combining rule that is well defined. In this paper, basically, he suggested that each of those completed data sets could be distributed as a data that is privacy preserving, essentially, right? So now building up on that, in 2005, Rita basically in this paper basically proposed the use of classification and CAD basically in order to generate partially synthetic data, and so this approach is easy in the sense that you could essentially basically this approach actually breaks it down in such a way that you can propose a sequence of different univariate models using CAT, and then just to follow up on this, and then there's this paper that is from 2010 by Rita and his colleagues, where basically they propose this paper where you can do multiple imputation through like a series of different trees, basically. And this paper is useful in the sense that because if you were to do multiple imputation, in general, it is very difficult to propose like a fully conditional model for that is able to capture all of the data structures within the model. And so in this TAP paper, basically, they suggested that maybe you can propose a series of univariate models that could be combined instead of a single conditional instead of a single conditional model. So just based on these three papers, we know that if you're interested in generating, like if you're interested in data synthesis, there are two sampling frameworks that you could generally follow, right? Say, for example, we have some observed data labeled by Y, right? And that follows some probability distribution, and they are parameterized by theta. In order to use a plug-in sampling to generate this kind of data, all that you need to do is to, at first, you assume that some estimator of the observed value, right, is good enough for that data, right? So just to go back to the previous slide. So for example, here, if I have these continuous variables, let's say, for example, I have a missing continuous value, then I could, for example, use the mean estimator, right? Find the mean value and then substitute it there. So similarly for your plugin estimator, you can think of a suitable estimator for the observed value, right, in that column, and then just plug it back into the into that density. So basically you end up having the density, you end up having the density parameterized by theta hat. And then if you want to generate the synthetic copies of that data, I index them by Z. Basically all that you need to do is to sample from that distribution. So if it is a Gaussian, for example, you can sample from the Gaussian based on that new parameter. And so you can go on to generate M different copies to obtain M different synthetic data sets. If you don't want to use a plugin estimator, you can go Bayesian. So you can essentially go Bayesian. So again, if we assume that the observed values follow some distribution, again, parameterized by theta. Theta could be a scalar or a vector, it doesn't matter. We can assume a prior for that theta, and then just compute the posterior. Then we can sample, we can basically take draws from the posterior to going from theta 1 up to m, which was m of them. And for each of those draws, we can generate like synthetic data sets by sampling from the PDF that is now parameterized by these posterior draws. Okay. Yeah. So now just to go over some of the common use cases for this. So perhaps two of the biggest use cases would be privacy and data enhancement. So in terms of privacy, we can think of internal data use. Let's say, for example, you have data in a hospital or in a hospital, for example, or and you want to distribute the data within the hospital. Because of privacy concerns, and often because of that, you cannot just take that data and then distribute it across the network. But instead, one of the things that you could do is to generate synthetic copies of that data and then distribute them. Even if the patients agree that you could use the data, often passing the data onto a third party it could actually be a violation of that agreement. And so basically this approach could be a way of getting around that and ensuring that you're able to share the data without violating existing agreements. So another method is through data vendors. For example, you could basically encourage them to generate this kind of data, and then they'll be able to share it so that it could be used. Also for like teaching purposes, if you're interested in, for example, making your data accessible to like the community. So for example, you could generate like a synthetic version of your data and make that accessible even online. For the most part, you don't have to worry about privacy concerns, because with this kind of data sets, you don't have a one-to-one correspondence. So the data could be made available. And I have to say, I mean, now this is now the standard for most agencies. So for example, StatsCan or like different stats bureaus would typically generate this kind of data and then make it accessible. The other use case is data enhancement. This is our main interest in this talk today. Two areas of data enhancement that are often looked at. The first one is data augmentation. So for example, if you have a data set, let's say that has a small number of observations, it might be possible to generate like, it might actually be able to generate this kind of data and then augment it with the original data in order to increase the size. Or you could also generate a fully like synthetic version of the data and amplify it, generate like a number of copies that is much larger than the original cohort. In this work, we are interested in how we can use this kind of data in order to correct for imbalance or mitigate bias. So what do I mean by bias? Bias is quite a convoluted term, and I will try to define what I mean by data bias, the kind of bias we are interested in, and how they could actually be mitigated. So formally, I will define data bias as this, at least the kind that we are interested in. We say that a data is said to be biased with respect to a variable if the distribution of that variable in the sample cohort that you are working with is different from its distribution in the original cohort. That is to say that the properties of that sample is different from the properties of the population. So if you wanted to use that data set to do analysis, it will not reflect the original sample. So I present here a hypothetical example of a data set that shows sampling bias. So let's say we have some outcome Y, and then we have a group of predictors Z and X, right? This data will be considered to be balanced because if we look at like the two categories here, let's say Z here has two categories, Z positive and negative. So this could be, for example, a disease or something like that. Then among each of these groups, like Z plus, you have an equal distribution of your X's. You have X positive and X negative and X positive. You have an equal distribution. So one way, for example, to think about this, let's say, for example, you have males and females. You have an equal distribution of males and females in each of these categories. So this will be considered to be a balanced data. If we take a sampling, if we take a sample out of this, say, for example, this is in bias, we can take out some of these observations and then just work with the remaining. Now, it turns out that now, if you look at the bottom quarter, basically, if you look here, you will see that there's an uneven distribution, right? And so using this kind of data in order for you to do analysis would lead to your precision, like in terms of your estimate will be biased, you'll have inflated standard errors, and then you will not have like correct predictions in general, right? So, so some examples, for example, some popular examples would be gender, for example, where you typically have underrepresentation of a specific gender in like a data set. And these biases in general, they could result from a range of different things, right? During your, like all the way starting from recruitment, right? For example, they could be due to difficulty in access or like non-response, for example. So some of your participants may not respond. This could also happen during the data, like during the process when you are generating the data. It could be inherent in the process that you developed. It could also happen by excluding certain groups. So for example, always like a lot of the time, you always start up with one larger data set, and you can pick a sample that basically leads to this kind of imbalance. I just have to clarify that this is different from missingness. When, for example, some observations in some covariates are missing. Oh, by the way, if you have any question, please feel free to ask. I'll be more than happy to clarify. Okay, so in terms of the different types of data bias, we classify them into two different types. So you basically have this one called basically you have a marginal bias. That is essentially when your biasing variable. So for example, in the previous example that I showed, we have a biasing variable Z. That is when, for example, some observations in Z are excluded without independent of any other variable in the data, right? So solely based on Z, some observations are excluded. And then you have we consider two conditional cases. That is when, for example, some observations in the biasing variable are excluded, given an additional variable which is either correlated or not correlated, and those will be the two conditional cases. So you have conditional type 1 and type 2, right? So these are the three conditional cases of bias that we considered, and we could induce this by removing observations and then see how the method that is proposed would be able to mitigate for this. Obviously, it could be so it could be conditioned on two or more, but for simplicity, we just consider like a single conditional variable. So over the years, there has been quite a number of major events that have made headlines in the news because of data bias. Some examples that often come to mind would be some examples that would come to mind would be like in major employment, in major employment systems that were found to be biased towards certain genders. So for example, Amazon in 2018 had to completely scrape off like they basically have to completely scrape off like one of their like systems because of this. Another one is like is basically for treatment. So in some major US hospitals, like VA hospitals, basically they were using treatment systems that were found to be biased. Oh, okay, yeah, exactly, yeah. But yeah, so this was I mean, so like one of the reasons why this system was actually biased was that, so for example, we can think of a setting where, for example, we may have some health workers collecting data on like pain, for example, and they may ask patients, how much pain do you experience, right? So for example, some minorities might be allocated like a lower pain score. And then if we use that data, I mean, for our systems, then it would in turn lead to bias settings, right? Another one is like in the prison systems. But in general, the point is not just underrepresentation. The point is that having an imbalance could lead to bias in one way or another. Even if you have overrepresentation, it might only be suitable for predicting that group and not any other group, right? So just to make that distinction. So over the years, various approaches have been proposed for mitigating data bias. Perhaps the most common ones would be, for example, like random oversampling. It doesn't sound much intuitive, but essentially what it involves is that, let's say you have a biased data, right? With a categorical variable that is biased. So oversampling, essentially, what it does is take some of those observations and then repeat them, right? And then the claim is that this will make this, like whichever model that you fit, it will be stable enough for you to be able to run it. Another approach that we looked at is essentially undersampling. If you have a data set with large enough people, you could also consider undersampling. So you take the group that is overrepresented, like randomly sample some of them and just exclude them, and then work with this new data cohort. So another approach that we also looked at is called smooth, which is a synthetic minor oversampling technique. It basically so basically it also generates like some new data based on the minority, but it uses like k-means as a way of getting to that. And then you could also use matching. So for example, if you're worried about matching, you can consider matching like the underrepresented and overrepresented categories. You can consider matching them on all the covariates. So propensity score matching would be one way of doing this. In fact, in epi studies, a lot of the time they tend to prefer using this kind of matching as a way of rebalancing. Like, okay, and so you can also use like ensembles in general. I mean, there's argument to be made about how stable they are compared to other methods. And then finally, we look at the approach that is proposed, which we call synthetic minor augmentation. So this augmentation method that we propose could essentially be performed in like 3 different steps. The first step really is to construct a synthetic version of the bias data. So basically we use light gradient boosting machines generally. So there's an argument to be made, like there's a lot of work that shows how these trees are essentially much better than other approaches. So for example, we know the CAT, for example, has gained a lot of prominence over the years, and it is quite frequently applied. But we know that in terms of accuracy, scalability, for example, we know that boosting trees perform much better. And then once you've generated that synthetic data, the next step really is to sample out of the minority class of that data, and then augment it with the bias sample. So at the end, you end up having a new data set, which is much larger than the originally biased data, with additional observations that are only like that were generated through this process, basically. Okay, so just to go over on how model evaluation was performed. So if we think about starting off with some original cohort, right, which is non-biased, right? So the results that there would be your ground truth. What we did essentially is to sample that data set into your training and test set. And then using that training data, we induce bias, so sampling bias, like all of the different sampling biases that we've talked about. So either the marginal or the 2 conditional cases, we induce it in that training data. and then apply the bias mitigating approaches. So random undersampling, oversampling, smooth ensembles, and the minor augmentation that is proposed. And then once we've applied these approaches to next thing that we do is to basically just train them. We chose to use a logistic model because it's easy to interpret. So basically it is just easy to interpret, and it's accessible it's quite accessible to a lot of different people. And so we evaluate the model built on all of these approaches with the same test set, right? So in this sense, we can compare how the original training set on the test set compares to each of these approaches on the test set, basically. And in order to compare these models for predictive, if we consider prediction, we just consider the AUC estimate. In terms of etiology, so for example, we considered the OR estimate, like the odds ratio, and the associated standard error, and then confidence interval overlap. So we considered two applications. We considered a series of simulation studies, and we also assess how the approach performs on 4 real data sets, mostly from oncology. As I said, just like what I have said before, we basically considered a binary logistic and essentially okay, so and then for the data we basically assume that okay, so for the simulation setting we are able to ensure that from the start we have a balanced data set, and for each of the real data sets we also assume that that real data is our ground truth. This has some flaws, obviously, because it is possible that that real data set that we are working with already has some major bias in it, but that is what we have to work with. I mean, if it is large enough that we can do estimation, we assume that it is the truth, and then we induce further bias, perhaps, and then see how our approaches would basically perform on them. So in terms of the simulation settings, we assume a binary outcome data. Off the bat, we're able to ensure that so this Z here is our main variable of interest. We basically we simulated from a binomial probability 50. So there's equal representation of the two categories, and we basically propose 4 covariates, so x1 and x2, for example, and we are able to basically specify how much 1 and 0s we have in each of these categories, so Z1 and Z0, for example. And this is generally similar enough. We don't want them to be exact, but they're close enough, right? So 40% proportion and 35% proportion, right? And we fix our parameters. The main parameter that is of interest is an odds ratio of 1.25. And so we postulate a logistic model that involves mostly some linear terms and one interaction term, essentially. And U here is just a continuous variable that is highly predictive of the outcome as well. And so we generate 5,000 observations. We repeat this 500 times. So in terms of some of the simulation results, so you can see that we have basically we have a missing proportion going from 15% to 50. I saw results out of 50%, but you can go further. And for the original cohort, the optimal value for the AUC is 0.772. The odds ratio that we fixed was 1.25, and then using the original cohort, we can estimate it to 1.24. And this is the standard deviation from the multiple repetitions that we've done. And the confidence interval overlap has an initial value of 1, so overlap with the original cohort, right? And so basically, you can say that even for low amount of bias, like 15%, we have an odds ratio estimated to be around 1.30. And once we've mitigated for the bias, we are basically able to recover the true estimate to like 1.25 with a slightly smaller standard deviation. And in terms of confidence interval overlap, you go from 96% to like 98%. This is still a very low amount of bias for a data set that is large enough. And then in terms of the conditional cases, again, we see that like consistently, we can say that the approach that is proposed outperforms using a bias data or any of the other bias mitigating approaches. In some cases, I have to say, for example, in the second conditional case, where, for example, observations are removed based on the biasing variable along with a strong predictor. In that case, for example, like using matching, for example, tend to perform like quite well, especially when the bias is a little bit high. And so as we increase the missing proportion to like 30% and 50%, again, you can see that consistently the approach is much better than any of these competitors. So the next thing that we did basically was to stratify the analysis as well, just to see, for example, how well can we predict the biased group, right? Let's say, for example, we have male and female, and female is under. So basically, we like divide the data and then use the data with only female subjects and see how well we can do prediction for only the category. And so again, and basically we did this for different odds ratios, starting from very low level odds like 0.5 to 1.5 to 2.0. And then you can, in general, you can see, basically what you observe is that when it comes to like prediction, you don't see a lot of gain in terms of in terms of improvements in terms of AUC. So it is what, like, just to know that, like, in terms of AUC scores, you wouldn't see a lot of improvements, but in terms of estimating the effect, you will tend to see a lot more drastic change and improvement, obviously. So the next thing that we also assessed was to look at fairness in terms of in terms of parity difference. So basically, that is to say that how well can you predict the outcome given someone is in one category versus the other, given that the true value of that outcome is in fact positive, right? So how can you predict a positive value given that it is truly positive if the person is female versus male? So in a very optimal setting, this value will be 0, right? We know that the outcome is positive. If the person is female and they have a positive outcome, then you should be able to predict a positive outcome. So we measure this difference. And then again, you can see that both in the marginal and conditional cases, you can see that the approach that is proposed, synthetic minor augmentation, it almost always outperforms the other approaches, right? So you get a better fairness in terms of comparing the different groups. So we basically considered like 4 different case studies, but I'll present results for only one. That is this colon cancer data. The data involves about 1,500 observations, 10 variables, and the outcome of interest was that. So the main predictor that is of interest was bowel obstruction. The amount was actually quite, so those who did not have this condition were like 83.8%. And we considered, so in the marginal case, observations would be removed only based on bowel obstruction. In the 2 conditional cases, it will be conditioned on gender as well. In the second one, it will be conditioned on BMI category as well. So there are different categories. So just to quickly show you the results, it's a little bit similar. And again, even for this, you can see that the approach that is proposed basically outperforms, especially in moderate cases, up to 50%. You can see that compared to the optimal value, where the odds ratio is 0.5 and the standard error is like 0.3, you can see that we are much closer to the optimal value than any of the other approaches. So you get like 0.62 here. And then if you use matching, you get like 2.48, right? So which is like quite encouraging, right? So we are consistently outperforming all the methods that we are comparing. So again, in terms of like predictions, so we have AUC on this column, and then we have different bias in proportions. So for the ground truth data, generally it was like 0.75, and that is a green line. And so you can see that our approach, which is highlighted in red, basically performs quite well compared to the other approaches. In extreme cases of bias, the results are generally inconclusive. It is not clear which methods outperform which, but that is understandable, perhaps because you don't have enough observations to even do a proper modeling. So again, in terms of the fairness metrics, almost consistently, our approach does quite well, much closer to 0 compared to the other approaches. Right? It could be biased, it could be negative or positive. It's closeness to 0. So some observations that we've made throughout this work is that generally you wouldn't see a significant difference in terms of AUC estimates when it comes to bias. It has to be really extreme before you begin to see some shifts, right? But the effect of bias is much more significant on the coefficients. And yeah, and then in general, the method that we propose works well in both absolute terms and relative to all of the different methods. It works in both low to moderate bias settings. When the bias is high, greater than 50%, then the results are not always obvious, generally inconclusive. And in fact, when you go to very extreme cases, you begin to get poor results for almost all of the different approaches. And again, the method performs well for fairness. So our method obviously has some limitations. It only works well in low settings. In extreme settings, then you basically are not able to recover what you've lost. We only applied our work to categorical data. Perhaps it is entirely possible to extend it to continuous values. And also in general, it improves if the analyst is able to decipher the bias in covariate and the conditional ones. You don't necessarily need it, but if you know it, that is additional information that could help you drastically improve the approach. Yes, thank you. And that is the end of the talk. I will be more than happy to answer questions.
Questions here or online? I just want to say if anybody has a question online, they can either unmute or I'll keep an eye on the chat. And there is actually a question in the chat. Sasha, do you want to turn on your microphone or would you like me to repeat it?
Sure. So thank you so much for that presentation. And so it's just a general question. So I myself look forward to hopefully doing some analysis. I'm a clinician and I have a PhD in epidemiology, and I look forward to using synthetic data at some point. I hope in the near future. But it seems to me we don't always know for sure if. I guess we assume, if I followed you correctly, that people, if women or Blacks are missing from a data set, that those who are present are truly representative of the whole population of women or Blacks or whatever. And I'm wondering if for me, it would seem like in reality, it may actually be that those who are represented within that data set might be special because they managed to get into the data set despite the fact that the things were stacked against them. So that is, do you yourself, have you thought about that? Do you think that that tends to be a nagging concern, or any comments on that?
Oh yes, yes, absolutely. So I mean, it is quite possible that, well, yeah, it is quite possible that those who are in the data set are actually representative of the real data, and that is not really an issue for us. So what we try to do instead is that if we have an imbalance, let's say we have different proportions of the different genders, for example, we just have to make sure that we have, for example, so basically the method is essentially taking the characteristics of those who are already there and then just increasing the number. So the same effects that you will estimate, right, even with that low number, would still be the same as if you were to rebalance it, right? So the effect doesn't, yeah. So I hope that clarifies. So just increasing increasing the number doesn't really change the true effect, but instead you are basically increasing the power in such a way that you can be able to do those estimations and have results that you are confident about. I guess so. I hope that answers your question. Yes.
Yeah, so like, let's say your NAMs are correlated with some variable, so you tend not to observe like the output if an input is like a certain range of numbers, or let's say it's harder to find female patients that have this disease for whatever reason, and so you don't incorporate them into your study. Like, why don't you just say that, well, the domain of the model is just narrower than encompassing like all the genders that exist, and just you only have patients in the male category, so just provide a model that works for males, and then you realize that, okay, I need to go do an empirical study where I focus on females. Like I personally, I don't believe that this synthetic data, I mean, especially like if you were to replace like NAMs by, as you said, like the mean, the sample mean, like that's going to reduce the standard deviation of that value in the column. And that variability is very important. It seems like you are totally limited by the information that you collected empirically, and no amount of synthetic data is going to like increase the amount of information that you can extract. Like the only way you can do that is go out in the real world and do more experiments.
Yeah. So to some extent, real world data is would definitely be the gold standard. Let's put it there. The problem though is that a lot of the time we do analysis and then include like underrepresented categories of other groups, right? If you were to just do analysis and then completely exclude that category, then that's fine. But if you do analysis with an underrepresented category, then you end up obtaining results that are not that are not good enough, exactly, right? So for example, it could happen that the estimates that you obtain could drastically change if that number is increased. So that is why we have to make sure that we have enough observations of each category, right? And even better, if they could be balanced, then you could both do like predictions that are precise, and then your estimates will not be unstable.
Well, if your outcome is going to drastically change by increasing the number of samples in your underrepresented category, like how could you possibly know beforehand which direction that number is going to change in? I mean, like you don't. If you were to like increase the sample size artificially, you're making assumptions about what the data is. So validating that, because of course,
yeah,
that's what you've done.
So let me just clarify something. So the synthetic data is supposed to represent the data that you have. It is not a new addition, right? So that is why you always check that. Essentially, you check to make sure that all of the properties of the original data matches the new data. So all that you are doing is increasing those observations, but maintaining all of this, like all of the properties that are inherent within it would still be maintained. And by the way, this is now a standard across the board. Whenever you receive data, for example, from StatScan, you never receive real data. It is always synthetic data. It is the gold standard in all the major agencies. No one is going to, and this is born, it could be for privacy reasons and also like data enhancement purposes, but synthetic data has become standard over the years. Like that is on this feature.
It's an interesting thing.
Yeah.
It's an interesting thing to think about, but it's
Yeah. Yeah, please.
About
Yeah.
the safeguarding aspect, like missing values,
Mhm.
one, or whatever heuristic you go with.
Mhm.
But then where are you just adding noise to the already existing values so that they're different from the?
Yes,
your
syn-
actual data?
So, well, there are techniques that allow you to add noise, right? So, for example, if I were to do like, if I wanted to, if I wanted to include like differential privacy, for example, I might consider like noise addition. But in this case, essentially all that we are doing is that we are taking the data, modeling it, right? Finding a suitable model, and then we've estimated the parameters. And we are saying that if we take some arbitrary samples, right? Some fake female, male this, right? And then if the model is good enough, then we should be able to predict a target, right? That matches those features, right? And so at the end of the day, you're able to get a new data that preserves essentially the properties of the data itself. And you can do this either through a Bayesian sampling or some other means.
Wouldn't those properties just like be what they are because of the low sample size? Like if you say that increasing the sample size changes your parameter prediction, then the reason why they were different at low sample size is just because of like the fluctuations you get from sampling.
Yeah. Yeah, so yeah, no, that's a very good point and a valid one indeed. A lot of the time when we do analysis, for example, if we use like a linear, if we do like logistic or linear, for example, we are prone to be faced with challenges in terms of sample size. But the difference here is that when we are generating, when we are essentially like generating this, we are doing it like we are doing it in basically we are basically breaking it down into smaller univariable models. For example, when you use CAT or light boosting system, what we are essentially doing is we are essentially like using models that are better suited for sparse data, essentially. So the argument that the argument is that using some of these more robust models, we can generate copies that could later be utilized for models that are less robust. So, for example, your linear regression or some other, for example, so some deep learning model which need a lot of data, for example.
I mean, are you making an implicit assumption that the
That-
truth is a relatively simple model without a lot of high order interactions?
Not necessarily,
Not necessarily.
not necessarily, but instead we are saying that using some of these non-parametric techniques, in particular using like trees or CAT, for example, you are able to model like some of these data. You're able to capture like within data complexities much better with some of these models,
Yeah.
right? And once you are able to expand that, then you can basically like just augment it to your data, and then like all the extra analysis, for example, like when you do when you use like other models that are more data hungry, then you will be able to do the estimation much better. Yeah, that's kind of the argument again.
Are there other questions from those who are online? Or in the room? Okay, well then I'd like to thank Lamin for a really interesting presentation and challenging us to think about our sources of bias and how to deal with them. Thank you very much.
Thank you so much. Thank you.